All right, so section 4.5, the dimension of a vector space. We begin our lesson with theorem first, okay? Theorem 10. Please read the theorem very carefully. If a vector space V has a basis B equals B sub 1, B sub 2, all the way up to B sub n, then any set in V containing more than n vectors must be linearly dependent. Now remember, we define basis in our last class. Basis means it's efficient vector, so linearly independent vectors. Okay, so if basis B, basis for vector space V is B sub 1, B sub 2, all the way up to B sub n, that means n, there are n linearly independent vector. Then if you add any other vector, let's say Bn plus 1, for example, then that means this is linearly dependent now. Okay, so any other extra vectors will be linearly dependent. That's what the theorem 10 tells us. So basically what it tells us is that if basis for the vector space V is B sub 1, B sub 2, all the way up to B sub n, then there are n linearly independent vectors. Okay, keep that in mind. Now let's look at another theorem. If a vector space V has a basis of n vectors, then every basis of V must consist of exactly n vectors. Remember, the vector space V has basis of n vectors. There are n linearly independent vectors. Then every basis of V must consist of exactly n vector. By the way, and this n is called the dimension of the vector space. Okay, so later on we will talk about the dimension of the vector space. So dimension of the vector space means linearly independent vectors. In another word, you can also say that dimension of the vector space is number of basis vectors. Okay, dimension of the vector space V is number of basis vector, or you can say linearly number of linearly independent vectors, or you can say if there are n linearly independent vectors, then that will be n. Now let's look at the definition. If V is spanned by a finite set, then V is said to be finite dimensional. Okay, V is a space. Remember, V is a vector space. Think this as a container which is generated by a finite sets. Then V is said to be finite dimensional, and the dimension of V, written as dim B, is the number of vectors in a basis for V. Okay, the dimension of the zero vector space is written as 0 is 0. Okay, if V is not spanned by a finite set, then V is said to be infinite dimensional. Okay, now let's look at example 1. So we are given a vector, vector space H, which is spanned by V1 and V2, where V1 is this, V2 is this. Find the dimension of H. Now we just define that dimension of the vector space is the number of linearly independent vectors in the space. So look at that, V1 and V2, are they linearly independent? Yes, they are, because they are not multiple of each other. When we are given two vectors, then to figure out whether they are linearly dependent or independent, it's pretty easy. If they are multiple of each other, linearly dependent. If not, then linearly independent. So the dimension of H equals 2 because v1 and v2 are linearly independent. Okay, that's it. Now let's look at some examples. You know that the standard basis for Rn is written as E sub 1, E sub 2, all the way up to E sub n, and this contains n linearly independent vectors. Therefore, dimension of Rn will be n. Okay. By the same token, dimension of R2 is 2, dimension of R3 will be 3, and so on. Let's look at one polynomial. Okay, since the standard basis of Pn is 1x, x squared all the way up to xn, so dimension of Pn will be n plus 1, because you see that this is 1, 2, 3 all the way up to n, and there is one more vector, and they are linearly independent. You can prove it easily. So the dimension of Pn, polynomial of degree n, equals n plus 1. By the same token, dimension of P1 is 2, because in order to generate a polynomial of degree 1, that means 1 plus a0 plus a1t. Okay, so that means 1 and t is the standard basis for P1. So there are two linearly independent vectors. For P1, 2, in the same way, dimension of P2 will be 3, and so on. Okay, now let's look at another example. Example 2. Find the dimension of the subspace H spanned by these, okay, given by this matrix. So all you need to do in this case is try to figure out what are the vectors there that span H. So you can write this. Let X is in H, then X can be written as a minus 3b plus 6b, 5a plus 4d, b minus 2c minus d, and 5d. So this can be written as a plus b plus c plus d. Okay, a is here 1, 5, 0, 0. Okay, in the first one there is a there in the first row and a there in the second row, and so on. B will be negative 3 and 0, 1 and 0. C will be 0. So this one 6. This is, guys, this one is, I believe this one is 6D or 6C. This is 6C. There is a typo. Please make necessary correction. This is 6C, okay? A minus 3B plus 6C. So C will be 6 and then 0, negative 2, 0, and D 0, 4, negative 1, 5. Okay, so that means what we can say is that H is the span of all these vectors. 1, 5, 0, 0, negative 3, 0, 1, 0, and 6, 0, negative 2, 0, and 0, 4, negative 1, 5. All you need to do here is check whether they are linearly dependent or independent. Okay, so how can we check that? We consider a matrix, right? So consider matrix A such that this one is, let me just write it down as this is my, let's say v1, v2, v3, and v4. So consider matrix A, which will be v1, v2, v3, and v4. What that means is, this means 1, 5, 0, 0, negative 3, 0, 1, 0, 6, 0, negative 2, 0, 0, 4, negative 1, 5. Now, to check whether it's linear, the vectors are linearly dependent or independent, or how many vectors are linearly independent, what you need to do is change it into echelon form. Okay, change to echelon form, and I'll wait for you guys. So please change it into echelon form and let me know. So if you change this into echelon form, okay, I'm going to change it into echelon form, and this is what I got. The first one is negative 1, negative 3, 6, 0. And I got so as we have seen in this one is in echelon form, and we have observed, we have seen that there are three basic variables. Okay, there are three basic variables. That means there are three pivot columns, and that represent the linearly independent vectors. So dimension of H equals 3 because there are three linearly independent vectors, or you can say three basic variable, or you can say three pivot column. They mean the same thing, pivot column. Okay, so the dimension of H is 3. Okay, I want you to do example 3 on your own just for fun. So the vectors are already given, so you can consider matrix A, which is 1, negative 5, negative 2, 10, negative 3, 15. Remember, all we need to do is we need to check how many vectors are linearly independent there. We know that there are three vectors given. So among those three, how many are linearly independent? Okay, so all you need to do is change it into echelon form. Change to echelon form. And that's going to give me since there is one pivot column, in another word, since there is one free variable, that means there is one linearly independent vector. So therefore, dimension of H equals 1. Okay. Theorem 13, the basis theorem. Okay, let V be a p-dimensional vector space with p greater than or equal to 1. Any linearly independent set of p vectors in V is a basis of V. Any set of p vectors in V that span V is a basis of V. So I think we will discuss this more detail with example later on, especially when we look at example 5, uh, then you will understand this basis theorem better. Okay, uh, so let's focus our attention at this point for example 4, and then once we try to solve example 5, then we will take help from this theorem 13, the basis theorem. So example 4, so that the set of vectors is a basis of P2. Okay, we need to show that the basis of P2. I believe you can do this by yourself. We have done this kind of problem in chapter 1. I think I leave it to you. I trust you guys that you can do it by yourself. I leave it to you, and let's move forward. But if you need help, then I will provide the detailed solution in my lecture note. Okay. All you need to do is that if this one is the basis, that means you need to show that they are linearly independent. That's all you need to do. Okay, so that they are linearly independent. So now we focus our attention on three important space and their dimension. Okay, we will focus our attention on three important space and their dimension. What are those? Dimension of null space, column space, and row space and their dimension. Okay, now first let us look at the definition. Here is the definition: rank and nullity. What is rank? The rank of A is the dimension of the column space of A. Okay, so dimension of column space of A is called the rank. Since row space of A is the same as column space of A transpose, the dimension of the row space of A is the rank of A transpose. By the way, we will talk about this in a minute, but please remember, dimension of column space of A equals dimension of row space of A equals dimension of column space of A transpose equals dimension of row space of A transpose, and that is called rank. Okay, please remember this, and you can verify, you can prove this very easily. If dimension of column A means equals, let's say, n, for example, that means there are n pivot position. So the pivot position determines the dimension of column A as well as dimension of row A, and column A transpose is actually the that is the row space, and dimension of row A transpose is actually the column space, because when you transpose, row will change into column, column will change into row, and they all are equal, which we call rank. And now another word, very important word, nullity. What is the nullity? Well, nullity means it is the dimension of null space of A is called nullity. So dimension of null space of A is called nullity. So we define two words, rank and nullity. Now, what is row space? You know, the column space means it's the space is spanned by the column of A, right? So we know that column space of A means is span, it is generated. This is a space that is generated by the column of A, columns of A. Okay, suppose A equals, let's say, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. then column space of A will be the span of column of A. Column of A means 1, 2, 3, 4, 5, 6, 7, 8, 9, provided they are linearly independent. And row space of A is the space. By the way, this one is, they all the three vectors, I intentionally choose linearly independent vectors. Okay, keep that in mind. I intentionally choose this linearly independent vector. So column space of A is the span of the, linearly independent column of A. So row space of A is the span of linearly span of the rows. So 1, 1, 4, 7, 2, 5, 8, and 7, 8, 9. No, sorry, 1, 4, 7. This will be 2, 5, 8. Yes, 2, 5, 8, and this 3, 6, 9. 3, 6, 9. This is called row space. Okay, it is a space generated or created by the rows of A. Okay, now here is one theorem. Oh, by the way, a rank we already discussed. Rank means its dimension of column space or dimension of row space, which is actually the number of basic variable. Okay, number of basic variable, dimension of the vector space. We discussed that already. Now, what is the nullity? What is the dimension of null space? Dimension of null space is actually the number of free variable. Please remember, dimension of null A is called nullity, and that means number of free variable. So dimension rank means number of basic variable. Okay, now you need to memorize this. Rank means number of basic variable, and dimension of null A, which is nullity, is number of free variables. Keep that in mind. Now, here is one important theorem. We call it the rank theorem. Okay, the dimension of the column space and the row space of an M by N matrix A are equal. I think we already discussed that. Dimension of column space and dimension of row space are equal. And the common dimension, we call it rank of A, also equals the number of pivot position. That means number of basic variables in A, and satisfy the equation. Rank A, number of basic variable, plus dimension of null A, number of free variable, should be equal to N. Just keep that in mind. And proof, please check my lecture note, or you can check the proof in the textbook. It's pretty simple proof, by the way. Okay, let's do the proof just for fun. Okay, theorem 14, the rank theorem. So what we need to prove is, we need to prove that rank A plus dimension of null A equals N. So remember, the matrix has M by N matrix. Okay, so let A be an M by N matrix. Okay, then we know that rank of A equals dimension of column space of A, which is number of pivot columns, or you can say number of basic variable. Also, you can say column of A, or you can say number of basic variables. Okay, we know that. And we also know that dimension of null A, which is nullity, is number of free variables. In A. Okay, and we know that, and we also know that number of basic variables or number of pivot columns, you can say, number of, remember the free variable means, number of free variable means non-pivots, or you can say number of non-pivot column. Okay, they are the same thing. Free variable means non-pivot column. So we also know that number of pivot column plus number of non-pivot column must be equal to the total number of column, and the total number of column is n equals total number of column, right? We know that number of pivot column plus number of non-pivot column must be the total number of column, and number of pivot column is actually, we have seen that is rank A, plus number of non-pivot column is actually the free variable, which means it is the dimension of null A, and the total number of column is actually n for m by n matrix. See here, we are considering m by n matrix, so the total number of column is n, so it's proved. Okay guys, now we have the rank theorem, and using the rank theorem we will solve this example 5. So in example 5 we are given a matrix A, which is the size is 1 2 3 4 rows and 1 2 3 4 5 columns. So 4 by 5 size matrix is given. So that means our n equals 5 and m equals 4. Okay, there are 5 columns and 4 rows. Now we need to find the dimension of row A, column A, and null A. So all you need to do is change the matrix into echelon form in order to figure out dimension, right? Because dimension of column A means linearly independent column. So just change it into, to find dimension of row space of A, column space of A, and null space of A, change matrix A into echelon form. Okay, so let me just copy the matrix here. A is -2, -5, 8, 0, -17, 1, 3, -5, 1, 5, 3, 11, -19, 7, 1, and 1, 7, -13, 5, and -3. And change it into echelon form. And let me denote that echelon form by B. Okay, first thing I will do row 1 and row 2, I will interchange. So that's going to give me 1, 3, -5, 1, 5, and -2, -5, 8, 0, -17, and another is 3, 11, negative 19, 7, 1, another 1, 7, negative 13, 5, and negative 3. Now I want to change this into echelon form, and I trust you guys, you know how to do it. I just leave it like this, dot dot dot, and then I just need the final form. So the first row will remain the same, 1, 3, minus 5, 1, and 5, minus 5, 1, and 5. And okay, this is what I got. I got 0, 1, negative 2, negative 2, and negative 7, and 0, 0, 0, negative 4, and 20, and 0, 0, 0, 0, 0. This is what I got, okay, echelon form. And now part A, we need to find, okay, let me answer part A. Find the dimension of row A. So dimension of row A equals, remember, dimension of row is number of pivot columns, number of pivot columns, which means number of basic variable. Okay, number of basic variable. So that means number of basic variable is pivot column. Okay, so there is 1, 2, 3. Okay, there are 3 basic variable. So number of pivot is, this is our pivot, this one is pivot, and then this is pivot. So there are 3 basic variable, which means dimension of row is 3. Dimension of column A is also 3, because we know that, because dimension of row A equals dimension of column A, we already know that. And then dimension of null A equals number of free variable. Free variables. So number of free variables are, as you can see, equals 2. And according to the theorem, you can also use the rank theorem, because the n is, m by n. So m is 1, 2, 3, 4 by 5. And when n is 5 and the rank is 3, then you can use that theorem. Okay, you can use the theorem as well if you like. Alternatively, yeah, the theorem tells us that a rank of A plus dimension of null A equals n. So rank of A we already found 3, and dimension of null A we need to find that, and n we already know 5. So that means dimension of null A equals 5 minus 3 is 2. You can do this way too. Okay, so I would say this, method 1 for dimension of null A, and method 2 for dimension of null A is this, method 2. So part A we are done. So now part B, we need to find the basis for the row space of A, column space of A, and null space of A. Let me denote this echelon form of A by another matrix B. Guys, please listen very carefully, okay? So A is the given matrix, and we change it into echelon form, and I'm representing the echelon form of the matrix by another letter B. So this is my matrix B. Now in part B, find the basis for the row space. How do we find the basis of the row space? We know that basis for a row space of A is given by row with pivot. Okay, so that means basis for the row space is the row with pivot in the echelon form. That means in the echelon form means in matrix B in our example, matrix B. So that means it will be row space of A. Basis for the row space of A is basis of row A equals, so row with pivot, so the first row, second row and third row, so these are the rows with pivot. So first row is 1 3 5 negative 5 1 3 negative 5 1 and 5, and second one is 0 1 negative 2 negative 2 negative 7, and then 0 0 0 negative 4 and 20. So this is the row space of A. Okay, and now basis of column space of A. So column space of A is the column, pivot column from the original matrix, from the original, which is matrix A in this case. So that will be pivot column is column, first column, second column, and fourth column. So go all the way to the original matrix and write down the first, second, and fourth column. So the first column is negative 2 1 3 1, and then second column is negative 5 3 11 and 7, and then the fourth column is what is the fourth column? 0 1 7 9. Okay, 0 1 7 5. So this is the basis for a column space of A. One thing very important to keep in mind, basis for the row space we consider from the echelon form. Okay, rows with pivot from the echelon, but basis for column space will be pivot columns from the original matrix A, not from the echelon form. Why so? Think about it. Okay, I want you to think why we need to go back to the original matrix, and we'll discuss that later. Okay, now the third one is basis for null space. Okay, let us find basis for null space. I'll do it here. To find basis for null space of A, write the general solution. Okay, write general solution. And so the general solution will be general solution, maybe I can say so the general solution will be x1. Let me see. This is my x1, x2, x3, x4, x5. So it will be x1 plus 3x2 minus 5x3 plus x4 plus 5x5 equals 0. And the second one will be x2 minus 2x3 minus 2x4 minus 7x5 equals 0. And the third one is minus 4x4 plus 20x5 equals 0. Okay, general solution. Now this gives me x4 equals 5x5 in the same way, and then here we know that x3 and x5 are free. x3 and x5 are free, so they are free variable. So you express the basic variable in terms of free variable, okay, and let me know what you get. So expressing basic variable in terms of free variables, we get x1 equals x2 equals x3 x4 x5. I want all of these. Anyway, I believe you can express the basic variable x1, x2 and x4 in terms of free variable x3 and x5, and the result will be, this is what I got, it will be negative x3 minus x5, and x2 is 2x3 minus 3x5, and x3 is free, x4 is 5x5, and x5 is free. So that means any x can be written as x1, x2, x3, x4, x5 can be written as negative x3 minus x5, 2x3 minus 3x5, x3 is free, 5x5, and x5 is free. So we can write this way, and now I can write this way. So x3 means there will be negative 1, 2, 1, 0, 0. And for x5, I will have negative 1, negative 3, 0, 5, 1. Okay, so hence these two vectors represent, the basis for the null space. Hence basis for null space of A is these two vectors. So negative 1, 2, 1, 0, 0, and then negative 1, negative 3, 0, 5, 1. So they are the basis for the null space. All right, that's how we find basis for the null space. So far in this lesson, what we did is we started with the definition of dimension of a vector space, and then we talk about column space, row space, and null space, and then we learn how to find the dimension of column space, dimension of row space, and dimension of null space. Okay, we talk about rank, which is actually the dimension of column space or dimension of row space. And then we learn how to find the basis for column space, basis for row space, and basis for null space. So far, this is what we have done in this section. Okay. Now we look at the relationship between rank, nullity, and the number of columns and number of rows as well. We'll see the relationship between those. Let's look at example 6. Suppose a 4 by 5 matrix A has rank 3. So remember, example 5, So it is a 4 by 5 matrix. So A is 4 by 5. That means this, the matrix A will be something like, anyway, it's there will be 4 A1 1 A1 2 A1 5. This will be A2 1 A2 2 A2 5 A3 1 A3 2 A3 5 A4 1 A4 2 A4 5. So this is the type of matrix, right? So there are 2 columns there. Okay, so this is the kind. Now this matrix A has a rank 3. Remember here n equals, here n equals, it is m by n, so that means n equals 5. Keep that in mind. Now it has rank 3, so given rank equals 3, so we need to find the null space, I mean dimension of null A. Okay, so we know the formula. Okay, rank theorem. By rank theorem, we know that rank of A plus dimension of null space, dimension of null space of A equals n. We know that. So rank of A is already given, which is 3 plus dimension of null A we need to find, which is n is given 5. We already know that. So therefore, you can say that dimension of null A is 2. This one is done. Now you need to find the dimension of row A. So we know that dimension of row A and dimension of column A are same. So the rank 3 means dimension of row A is rank equals 3 equals dimension of rank A transpose as well, right? Because dimension of, rank of A transpose is actually the row, dimension of row. So they are all equal. So this one is 2, this is 3, this is also 3. Now the question is column A is equal R2? Column A. What is your answer here? Column A. Can column A be R2? No, because column of A has 1, 2, 3, 4 element. Okay, it should be in R4, not in R2. So next question is no. Column of A cannot be R2 because column of A has 4 entries, and so column of A equals R4. Make sense? So I want you to try example 7 by yourself, which means suppose, the question is suppose a 4 by 7 matrix A has rank 2. In example 7, a rank is given 2. And you need to find dimension of null A. Find dimension of null space of A, and then dimension of row space of A, dimension of rank A transpose, and then the question is column A equals R2? So these are the questions that you need to answer. All right, so the matrix A is given. Matrix A is of size 4 by 7. So that means n equals 7 given. N is given 7. In the formula, so using the formula, we know that rank plus null, rank plus dimension of null A equals n. So rank is 2 given plus dimension of null A equals n is given 7. Therefore, dimension of null A will be 5. Dimension of row A is actually called the rank, which is already given. The answer is already given there. Dimension of rank A transpose means it is the dimension of column, because, well, I think we already discussed that. So this also will be 2. And now the question is column space of A equals R2? The answer is, remember, the column is, there are 4 entries in column of A. Okay, if you just try to make a matrix A, it has 4 entry there, because 4 by 7 and this side 7. Therefore, it cannot be. No. Column A is actually R4. Right? It belongs to R4. There are 4 entries. Sometimes rank theorem is really helpful to figure out, whether the system has solution or not. For example, look at this example 9. Okay, application to system of equation. The rank theorem is a powerful tool for processing information about system of linear equation. For example, suppose the solution of a homogeneous system of 5 equations in 6 unknowns are all multiple of one non-zero solution. Will the system necessarily have a solution for every possible right-hand side, that is non-homogeneous system? Why or why not? That's the question. So it says that there are 5 equations in 6 unknowns. So what does that mean? A, B, 5 equations and 6 unknowns. So the matrix A will be of size 5 by 6. Okay. It is a coefficient matrix. Five by 6. 5 equations, 6 unknowns. So if you consider the coefficient matrix, it will be of size 5 by 6. Okay. And what is given is, okay, anyway, given. Also given that this are all multiple of one non-zero solution. So that means nullity of dimension of null A equals 1. That is given. Now I want you to find dimension of column A or rank. Okay, So by rank theorem, dimension of column space of A, or sometimes we call it rank of A, equals six minus 1, which is 5. Okay, see here, this one is your m by n, so n is 6, therefore n 6 minus 1, so that is 5. So dimension of column A or rank A is 5, which is actually also we can write dimension of row A, row space of A. What it means is there are 5 rows. Okay, this is 5 by 6, and then A is, there are 5 rows. So A1 1, A2 1, A2 3, A3 1, A4 1, A5 1, and this is the kind of matrix there. So dimension of row A or rank A equals 5 means there are 5 pivot columns. All right, so there are 5 pivot columns. So that means there are 5 linearly independent. So this means there are 5 pivot columns. This means, which means there are 5 linearly independent vectors. Okay, so there are 5 linearly independent vectors. That means if you have 5 linearly independent vectors with vectors, and each vector belongs to R5, because there are 1, 2, 3, 5. There are 5, entries belongs to R5 because each vector has 5 entries. So what it means is, so column of A equals all of R5. This means every non-homogeneous system of equation Ax equals B has a solution in R5, because actually there are 5 linearly independent vectors, and R5 has 5 dimensions. So you have that 5 linearly independent vectors. That means it will span, it will generate the whole space. That means every solution will be there.